Y'all. We'll be doing some quantum mechanics problems from Griffiths. I'll be going through some of the solutions. So I plan on going through several problems today before it's all said and done in chapters 2 and 3 and maybe 4. So we're looking at some problems from chapters 2 to 4 in Griffith, looking at the solutions. So we'll go ahead and get started with 2.1. In a moment, I'll get that going. So this one is saying for normalizable solutions, right? The separation constant E must be real. Write E in equation 2.7. So I'll go ahead and write down the equations that's in question as well. So equation 2.7 will be this equation here. So basically the uh, psi equation, and I have it written there right now, but let me write it a bit more clearly. I'll actually start on the next page. So we have psi of t of x and t. So basically this is the full wave equation. Equals this will be the space part, and this will be the time part, which gives us the full solution. And welcome those who are viewing. Be sure to give a chat. Let me know you're here. Let me know if you have any questions. And I'm also on Discord if anybody wants to join the Discord at the link at the top. So this is 2.7, and he's saying for normalizable solutions, the separation constant E must be real. Write E in equation 2.7 as E naught plus I lambda. For both of those real, ensure that the equation 1.20 is the whole for all t. Lambda must be 0. So basically, we're going to rewrite this with a different variable. So this is going to then become psi x e negative I e naught plus t over h bar. And we want to show that equation 1.20 is the whole. So we write out number 120. We're going on real kindness. That's some quantum mechanics. So I touched upon this a little bit in my other stream today, but this one I'll go into more detail and actually solve some problems. So this is 120. So they're talking about the fact that the wave function must be normalizable. So if I'm measuring the position of a wave particle, if it exists, there's 100% probability it's going to be somewhere. So this equation here is a way of measuring the probability that the wave function exists somewhere which means this should be 100. And this is where the 1 comes from. So it's basically 1 dot as a percentage point. So that is basically 100%. And thus we can do this for 2 different locations and find the probability that the particle will be in that area. So if I wanted the probability of the particle between A and B, and this is negative infinity up here and positive infinity up here, and we take a little part A and B, I'll put A and B here, and this equation will give me the probability that we'll find the particle in that location. So they're saying that show that in order for this still to be normalized, they call this being normalized. In order for this to be normalized properly, lambda must be 0. So let's take a look and see what the solution says about this. So the normalization condition, as we saw before with equation 1.20, now this mod squared, they call this mod squared sometimes, is actually the complex conjugate of the function times the function. That's the meaning of that symbolism, dx. And our equation was psi x. So this would be the complex conjugate of that. Then e to the I, e plus lambda t over h bar. Then psi x e to the negative I e plus lambda t over h bar dx. So this is going to have to equal 1 in order for this to work. So I'll simplify this a bit. So basically I decompose the exponential and move the size around. So what's going to happen is the ones of I wonder why they're not distributing a negative. So this negative here, I distributed this negative to both of these, but I see that they're not doing that. Oh, I see. It's because of the I. Believe. Yeah. So I think I'm missing an yeah, I'm missing an I. So this should be I lambda. So it makes a big difference. So what happens is when I have an I already there, so basically this I in blue was the one that was from the original problem, because the original, the change is E naught plus I lambda. Overlook the I that was there, I lambda. So what happens here when I distribute this, I distribute this I here to both of these, and of having an I there, the here becomes I squared. And the same thing, I have a negative I there, and here becomes negative I squared. And I is the square root of -1. That's what that stands for. So I squared is -1. So what ends up happening is, I'll also write this again. So this I squared on the left becomes -1. So that becomes negative lambda t over h bar. And the one on the right here becomes -1 as well, but then there's a positive there. So this becomes um, a positive. Let me simplify this a bit differently. So the one on the left becomes negative. I know I'm going to end up with a lambda uh, t. So I'll put the negative on the h bar. So the one on the left will end up being negative. So I have negative h bar. And the one on the right, and did I add an extra e? Boom. The e naught, e naught, e naught, e naught. I did add an extra e there. Lambda t. So this one will become a negative there, a positive. Positive. So that goes out plus 1 over h bar. All right. Make sure this works out. So I think I'm missing something in my math here with this double, whatchamacallit. This one ends up being a negative in the exponent. This one has a negative ends up being a positive in the exponent. They should cancel. But in the solution, it doesn't seem to be canceling. It looks like they're doubling positively. So let's see what I'm missing here. So the complex conjugate on the left side takes a negative away. So that becomes positive. Okay, that's what it is. When I distribute this, no, I did do that. I was about to say I have to distribute the negative into there, but I did distribute the negative. Positive. I need to break this into one more step. Instead of writing the whole thing, actually, I'll just write the whole thing. We have negative infinity, infinity, psi, star, psi. So then I have e to the I e naught plus I squared lambda t over h bar e to the negative I e naught minus I squared lambda t over h bar dx, right? So that seems good so far. And I'll break these into two exponentials. We have psi star psi. So this would be e to the I e naught t over h bar, then e to the negative lambda t over h bar. That would be, are they not getting a negative still? Why are they not getting a negative? Write something incorrect on the column again. Negative I e naught plus I lambda t over h bar. Oh, I see what I'm missing. I didn't put my negative on the, so when you do a complex conjugate, you have to change the sign of every imaginary number. So this is a negative imaginary number here and a positive there. So I have to, for the complex conjugate, have to make that positive and make this negative. That's what I was missing. So this one becomes negative on the complex conjugate side, and on the other side, it stays negative and positive. So now I have this multiplied in is negative on this side. So that was the detail I was missing. When this multiplies in, I still have a negative here and a negative in front, negative here. So now both of those have a negative. So then when I multiply the I squared, that gives me a negative, so that becomes positive there. So basically this was the step I was missing here. Complex conjugate all i's. So I have to remember to make sure to put that on all the i's that are there. You don't normally see problems with multiple i's, but gotta get used to that. So then we have on this side e to the negative I e naught t over h bar, and then e, and this will be negative I here, plus a negative is already there, so that becomes a positive lambda t over h bar dx, all right? So now we can simplify like I was trying to do before. So that's e naught minus e, then e. Well, let me know if you have any questions about anything, real kindness, and I'll be happy to answer. So now we have e to the, that'll double that, 2 lambda t over h bar dx. So that's how it doubles. Just remembering to put the negative on all the i's that we have. So that one negative sign, uh, if forgotten, really throws a wrench in the problem. Right? So this becomes 1 because it's e minus e naught, so it's e to the 0. So now I have e to the 2 lambda e over h bar, and ergo negative infinity infinity psi dx. And this part here, as we've seen before in the original equation, that part there is this equation right here. So basically it's that times the exponential. So you have that times the exponential. Would you say real kindness? I didn't catch I see BB, but that's all I caught. And to make sure we're clear here, equals negative infinity, infinity, uh, psi star, psi dx equals 1, right? So now I have that negative infinity to infinity, psi star, psi dx, and that's going to equal this. And this has to equal 1, and it equals 1 only. T is not going to be 0, h bar is not going to be 0, 2 is of course not 0, so only when this equals 0 does that remain true. So now we've proven that. But it says the time independent wave function psi x, time independent, can always be taken to be real, unlike psi x of t, which is necessarily complex. This doesn't mean that every solution to the time independent Schrodinger equation is real. What it says is that if you've got one that is not real, it can always be expressed as a linear combination of solutions with the same energy that are. So if we have a solution to the Schrodinger equation that's not real, it can be expressed as a linear combination of solutions with the same energy that are real. So this goes to the idea that if we solve the time-independent Schrodinger equation, it's going to be negative h bar squared over 2m, second derivative, plus the potential psi equals e psi. So if we can solve this and get a solution to this, so the solution would be psi of x, and these are all psi of x's. So if we can get a solution to this, then we can sum these solutions to equate to any state. And that'll be the linear combination that can provide a solution for even unreal or complex solutions to the full Schrodinger equation, the time-dependent equation. So even a solution to the time-independent Schrodinger equation is not real. So apparently this is saying both of them. You can solve time independent and time dependent with a sum of energy eigenstates. Suppose I'm going to rewrite the time independent Schrodinger equation again. Distribute the psi. So suppose psi is a solution to the time independent Schrodinger equation. If we take the complex conjugate of everything, we find the following. Let me make sure you have what they want. So you might as well stick to psi's that are real. You might as well stick to psi's that are real. Hint, if psi x satisfies the equation 2.5 for a given e, so too does its complex conjugate, and hence also the real linear combinations. Let me write down equation 2.5. Currently, the time independent Schrodinger equation is 2.5. So they're calling this equation 2.5. So put boxes around the specific equations that we use. Also a 2.4, but we don't normally deal with the time one. But maybe I should write that just in case. So the 2.41 deals with time. See, so we're just supposed to prove this. I'm looking saying what do they want us to do? They want us to prove this as well, that this holds. They want us to prove that a solution to the time independent and time dependent Schrodinger equation, we could take a linear combination of the real and unreal parts, which is to say linear combinations of the psi and the complex conjugate psi. 2.5 is the time independent Schrodinger equation. So we want a psi that satisfies the time independent. And we want to see if the complex conjugate also satisfies the time independent. And we want to see if the linear combination of the two, and perhaps the linear combination of the two takes care of it altogether. I do notice that there's an I in front of that one. So psi should solve it. Psi complex conjugate should solve it. Psi plus complex conjugate should solve it. And they're saying I psi minus complex conjugate should solve it. Ch2 does its complex conjugate and hence also the real linear combinations, those two. So they call these real linear combinations. Right? Welcome for viewing. Anybody there, be sure to drop a line in the chat. Let me know if you have any questions. My name is Daryl Lee Berry Jr. doing some quantum mechanics problems all day today. And I may take a break at such and such time and come back after lunch or something like that. Right now we're on problem 2.1, part B. And we're going to prove this thing here. So this is 2.5. I'll copy this down. So suppose psi solves this. So let's complex conjugate everything. And we get negative h bar squared over 2m, partial derivative of x squared, psi complex conjugate, plus v complex conjugate equals e complex conjugate. And this is a time independent Schrodinger equation for psi r. I'll just call this 2.5.1. So psi star is also a solution. Therefore, psi star is also a solution. It's generally true that if we have two solutions for the time independent equation with the same energy eigenvalue E, we see that E is unchanged because you don't take a complex conjugate of E. Any linear combination, psi, right? Let me write that, since E remains unchanged in both 2.5 and 2.5.1, both psi and psi star are energy eigenstates of E. Therefore, any linear combination of psi and psi star are also energy eigenstates of E. So psi tilde, as the solution calls it, equals alpha psi 1 plus beta psi 2 also solves. With the same energy. So that means that for us to write this out as the solution does, thus all I did was expand psi tilde into its two sides. Then I expanded the two sides until it completely expanded to equations. So now I can group these up. Should be negative. Now I can further factor out this alpha. So now I took the expansion, the complete expansion on line 3, which is here, and I factored out the alpha and the beta. So now I have the fact that uh, you know that any psi, so basically this is psi with no subcomponent. It gives E with no subcomponent. Psi star with no subcomponent gives E with no subcomponent. So basically psi 1 will give E1, or at least E will still get the same. So I'm trying to break down this notation. Okay, that's what it is. I need to, I want to break this into 2. So I'll call this 2. So for 1, so we know that we'll get that, we'll get E with the same psi, because that's an energy eigenstate. So we can also go like this. It will give us the same thing by the same logic. So overall, this equals uh, E E alpha psi 1 plus E beta psi 2. And I can further simplify these. E alpha psi 1 plus beta psi 2. And we know from earlier that psi tilde is alpha psi 1 and beta psi 2. So we get E psi tilde. So this shows that this sum of 2 solutions that solve the time-independent Schrodinger equation also solve the Schrodinger equation. And if we have a negative here instead of a positive right there, it would all come the same way. We would just end up with a negative here, and it'll still end up being psi tilde. So basically, we consider the negative to be included in alpha and beta. They could be positive or negative numbers. It doesn't really matter, long as the number is there to encapsulate that variable. And for the explanation, I just use psi tilde to make a symbol for the new weight function. Okay. So looking at the second part, we have psi plus psi star and I psi minus psi star. So if psi is complex, then this will solve it. We showed that earlier. We showed that the complex conjugate doesn't affect energy. So the complex conjugate would also solve for the same E. So the linear combination will solve for it. Let me write that. I'll call this 3 and 4. So earlier showed that both psi and psi star are eigenstates of E. Thus, per the the psi tilde example, psi plus psi star solves. Uh, if psi is real, then psi equals psi star. Thus, psi minus psi star equals 0. And psi plus psi star equals 2 psi, which is, or a scaled psi. Because if it's real, then the complex conjugate will equal the same thing as the as psi itself, right? So I move on to C. Vx is even. Even function is something like i.e. cosine. Right? Sine of x equals negative cosine of x, even function. So we want to show that if the potential is an even function, then psi can always be taken to be either even or odd. Ah, awesome. Thanks for letting me know, real kindness. Thanks for coming back. Do you have any questions about the uh, first parts here? Actually hate proofs. Guess we got to do them sometimes. To show that linear combinations of psi, both real and imaginary, if they solve the time-independent Schrodinger equation separately, then they solve it in combination as well, whether they're real or unreal. And I guess that's why they put this I there to bring out the fact that it's complex. But if it's complex, it's going to solve it, just like how we showed here that the complex part, the conjugate, just a conjugation, does not affect E. Therefore, whether it's imaginary or real, it should still work. And now I'm proving that if V is real, or at least is even, then the function can be odd or even. So the hint is if psi x satisfies equation 2.5, which is the time-independent Schrodinger equation. Let me need to write that somewhere. If psi of x satisfies 2.5 for a given e, so too does psi negative x, and hence also the even and odd linear combinations. Okay, so let's see how they prove this. All right. So from part B, if in equation 2.5 right? So we have two eigenstates, one with psi x, one side with negative x. They both solve with the same eigenvalue e. If that, then psi x plus or minus psi negative x solves 2.5. So we figured that out earlier with this proof here. And maybe I should clarify that specifically. A minus b is included in the variable B. So we proved that earlier. So we would like to show that for an even potential, then psi equals psi to the negative x solves the in the time independent equation with the same E if psi does. Okay, sounds good, real kindness. So what they want us to do is they want us to we want to show that for an even potential, show that for even potential v of x, which again means that, well, got that earlier, even means that v of x equals v of negative x, just like cosine. Psi tilde equals psi negative x. We want to show this solves the time-independent Schrodinger equation with the same eigenvalue, E, if psi of x does. I'll start that off, and instead of writing I define my psi tilde. I define that as psi to the negative x to save on some writing. So now we have interesting. So what we're going to do is I'll call, let's say, psi tilde is the one with the negative x. And we'll say that psi, so the v of x is even. If I define v of x as v of negative x, since it's even, v tilde equals v of x. So we could just call v of x just v of x through the whole thing. Uh, so to simplify this, if I distribute these psi, so we have that. We're going to evaluate psi double by repeatedly using a chain rule for f v of x, with f equals psi and g equals negative x. So basically, we're going to actually figure out what psi tilde is doing that actual second derivative. So basically what I'm going to do is I'm going to extract this out. So the first derivative is going to be partial x of psi prime negative x. Then I have to take the derivative of the inside. So it's going to be -1. And then that's going to equal the partial to derivative x. I should say, what is the best place to put it? Negative psi prime negative x. If I take another derivative, that's going to be negative psi double dot of negative x. Then I got to multiply by -1. So that's going to equal psi double dot of negative x. And this equals psi double dot, all right? Psi 2 of the double dot. So the psi double dot negative x, double prime negative x equals the same thing as psi double prime with a tilde on it. So if I was to rewrite this, right? So we have that. I noticed on one part, I don't know if it was a mistake or not, but he didn't put the double prime on the other end. But this looks good. And psi 2 of the x is psi of negative x, which is what I just wrote. I think, of course, that's what he meant to do the first time. And Vx equals V negative x, since it's even. So we can say all of this equals finally the right hand side has functions evaluated at negative x. And sure enough, this right hand side, everything. All that, right? since psi satisfies the time-independent right hand, must equal. So all of this must equal which we know now equals E equals that. And we know from part A or B that either one of these will solve, and we assume that it did, that the positive or the negative both gave the same E. So this means this also equals equals that. So E psi to the negative X, E psi to the X, and E psi tilde the X. Yeah, so they're all equal. So therefore, a tilde right there. What tilde means is just a way of simplifying writing. So basically what's going on there is we have a psi that is a psi of negative X. So I just wrote it that way to simplify it. And I can make that more clearer. So just a way of simplifying notation. So instead of having to write psi negative X all the time, or even without the X, because sometimes you'll notice I just write psi, like right here, I just write psi by itself. But if I want to specify that I have a negative there, I would have to always write the X part because the X is negative. But to save me from having to write negative X all the time, I just defined it as psi tilde, unless I know what that means all the time. And here I'll just being explicit with it. And it's basically expanding it back out to what it was. So psi tilde double X, pulling it back out is psi to the negative X double derivative. And now we know that it equals that with the same E, and it equals that with no negative on the X. So basically this equals this because I defined it that way. This equals that because we proved that earlier with part B. Part B, we know that if it gives us the same energy eigenvalue, then we can sort of interchange them. We showed that here with this equations. If two different equations give you the solution to the same energy eigenvalue, we can sort of use a linear combination. So basically, alpha psi 1 gave me a solution, beta psi 1 gave me a solution, so I can linear combinate them. And also what they're saying is if this psi to the negative X gives a solution to the same energy eigenvalue as psi regular X, then it also gives the same solution if you put a negative Vx up in there. And that's what this last part is showing. Right? Because since this equals that with a negative in there, and it still equals the one with the positive X. So basically this is the negative X1 in V. This is the positive X1 in V. But since it gives us the same solution, we can just equate them right away. And the end would be, therefore, and negative h bar squared over 2m psi tilde x, which is again the psi to the negative x, plus vx. Right. So psi tilde satisfies the time-independent equation as well. So, but I mean, this is everything he did. So, but still, I hate proofs. It only in the very last part did we input the psi to the negative x. I mean, the v to the negative x. Oh, I see. I forgot. I forgot that v equals the same thing. We might need to add another line up in here. So this also equals this equals the one with v positive. This equals the same psi here. It solved it. So if I expand it, that still solves it. And technically that was a rewrite. They're probably just rewriting stuff, but this is what the solution says. But I hate proofs. Hope they don't give us a proof on the exam. Let's move to another problem. Hopefully we have a more calculation type problem. Let's see what the next one's about. Oh, let me erase what I did the first time. So it says show that E must exceed, oh crap. Let me try to find some kind of, okay, I'm just gonna skip this one and come back to it. Let's do an actual calculation type problem. And I just have to remember to come back to 2.2 before the day ends, but I have a lot of time. Let's do 2.5. And I don't want to do another proof again. I think that's 2 proofs already. So let's actually solve a square root problem. Let's see what they say for 2.5. So 2.5, the particle in an infinite square well has this initial wave function. A particle in an infinite square well has this initial wave function and even mixture of the first 2 stationary states. So we have an infinite well. So this is similar to what I was doing on the other stream, but now we'll go into more detail and I'll actually solve the full thing instead of sort of giving an overview. So we have an infinite square well. So this means that the potential here, v of x equals infinity, v of x equals infinity, and v of x here equals 0. So the particle is trapped inside this well. Just imagine this goes up to infinity, where it's too high for the particle to get out. Just draw it like this. Imagine this is going off into infinity. And has an initial wave function, an even mixture of the first 2 stationary states. So the initial state of the particle and the 0 is at time equals 0 equals a psi 1 x plus psi 2 x. So we're going to normalize it. That is, find a. It's very easy if you exploit the orthogonality of psi 1 and psi 2. Recall that having normalized psi of x and t at t equals 0, you can rest assured that it stays normalized If you doubt this, check especially after doing part B. So then want us to normalize it by finding out what A is. So going off of what we did earlier, we know that psi from negative infinity to infinity of psi squared dx equals, and technically this is a big psi, but t is 0. So that's the complex conjugate dx. And we know that this equals 1. So that means that it's normalized so that you have a 100% probability of finding a particle somewhere. So what we can do here is we can actually plug in those values. And did it tell us the length of the well? I guess normally we choose the length of the well. So I'm going to call this 0, x equals 0, and I'll call this A, pretty customary. And I'm going to actually show how to normalize one. So we have, so if I was to distribute this, it'll be A psi 1 x plus A psi 2 x. So we have A psi 1 x plus A psi 2 x complex conjugate A psi 1 x plus A psi 2 x dx. So now I have to multiply this out. And this is from 0 to A, since we're using the actual bounds of the square world that we made. So this becomes integral from 0 to A of A squared psi 1 squared plus A squared psi 2 squared. That has got the first and the last first, plus A squared. And the thing is, these don't have any imaginary parts. That's why it's not necessary to uh, put the actual star on them. So psi 1 of x is real, and psi 2 of x is real. The imaginary one would look like this, like it was psi xt would look like psi I and e to the I et over h bar. But at t equals 0, you just get psi I. So that's what's going on here. So basically, this will be the full equation, the full sine t. But it specifically said psi x at 0t, the initial state. And they gave us the equation of the initial state when t is 0, which makes the imaginary part go away. Therefore, maybe I can make it more explicit here by putting the zeros there. So the imaginary part goes away. So when the imaginary part goes away, then psi star equals psi. And thus I could just go ahead and put this in there with no star on it. And maybe I should put this on this line. And thus I could just square it because psi star equals psi because there's no imaginary part. No imaginary part at t equals 0. All right, so it's going to be a squared. The first last, we'll do the outer ones. So that's a squared psi 1 then plus a squared right, so we have that. So that's going to become 0 to a, and I can actually factor out a squared 0 to a, psi 1 squared plus psi 2 squared plus 2 psi 1 psi 2 dx. And we could break this into 3 integrals, and we will have a squared 0 a psi 1 squared dx plus 0 a psi 2 squared dx plus 0 to a 2 psi 1 psi 2 dx. And by orthogonality, this equals 0. And we know from earlier, I believe I called it, what did I call that equation? Or actually, we got it from the book. We went to the book equation. Equation 120, we know that equals 1 because those are the same size from equation 120. That equals 1. So this equals a squared 1 plus 1 plus 0. So this equals 2a squared, which equals 1. So this means that a squared equals 1/2, and a equals the square root of 1/2, or 1 over square root of 2. So this means that in order for this state to be normalized, meaning that we've properly scaled the wave function so that we get accurate values because we've scaled it such that the maximum potential we'll get is 1. So basically, I solve this integral over the full range of the well. The well goes from 0 to a. So if I measure for this particle over the full range of the well, if the particle is there and the particle there, so we know it's there, there's 100% certainty that I'll find it somewhere in the well because it can't get out. We put it there. So now the scaling factor here of a equals 1 over square root of 2. I have to multiply the scaling factor by psi to make sure that the values I get are accurate, so that if I measure, you know, this part of the well, I won't get like 500% probability. I will get the proper number, percent of it, so that I can get some accurate values of where the particle might be. And what that means is, if I were to measure the particle in pieces, like if I took the well and I measured the probability it will be in each of these sections, they're all going to add to 1. There might be only 5% here, and there might be 20 here, and there might be 70 here, and then it might be 5 again here. But still, it'll all add up to 100 as far as the probability that we can find that particle in the entire space. So that's the way that works. And that's how the scaling factor allows us to get proper values for the probabilities. We have to normalize. But the good thing about it is that we normalize a function at t equals 0. And I believe they said that here as well. Recall that having normalized at t equals 0, you can rest assured it stays normalized. We can double check it, but I'm fine with not double checking it. Like that. Right. So now we need to find, I think I did that already. Normalize. Okay, they want us to find the actual full equations. So B, find psi xt. We attach the time component, psi x0. So psi x t equals psi x and psi t, which equals uh, a psi 1 x plus psi 2 x psi t. So this is going to equal 1 over square root of 2 psi 1 x 0 plus psi 2 x 0 times e to the negative I. I need to, this is correct if I put an I here. And I got to distribute that. This is e to the I e1 c over h bar and e to the I e2 c over h bar, because each one has to have its respective energy component. Let me see, make sure I didn't make any errors anywhere. 2 psi 1 e. And I should have a negative on here because it's oscillatory in the square well. So last time I just went straight to sine as an overview example, but now we're doing the actual problem where we're starting with the exponentials. And the fact that we put a negative there is what makes it oscillatory. So I'll show that momentarily. So the way it works is e to the I theta plus minus equals cosine theta plus minus I sine theta. So let's see how this works. And it actually didn't solve for it. It just went straight to the solution. I guess I could do that, but I think it'd be good practice for me to go through it again. So we have e negative I u1, how to say ei, do both of them at the same time, t over h bar equals cosine negative, and actually let me simplify this first. Maybe I is a bad, I'll just say e naught. That works. So that becomes cosine e naught t over h bar minus sine e naught t over h bar. All right. And we have two of these. Maybe this is the wrong process for this. I hate when they skip a line. Oh, you know what? They didn't do that. let's split it up a different way. So they did. Oh, my bad. I was trying to do too much. So what they did was they have a sign in the solution, and they just realized that this is going to be a sign. So basically, the whole thing that I did on the example, they did the same thing. So they are using sign for the psi, and they're keeping this for the time-dependent point. So if I was to show that briefly, so I can remind myself, we need psi I of x for an infinite well, and the well goes from 0 to a. So psi I x is going to be a sine kx, because it has to satisfy the time-independent Schrodinger equation, which is negative h bar squared over 2m psi dot psi double prime plus v psi is going to equal e psi. In this case, v is 0 because it's an infinite square well. So we have psi double prime equals 2m e over h bar psi. And so that means that psi double prime equals k squared psi. And the fact that it's sine covers psi I 0 equals a sine 0 equals 0. So now I need to have, because my sine is going to output this, and to show that, we have psi 1i x is going to be a cosine kx times k. And I dropped off my negative, just reminded me. And we have psi double prime I x equals negative a k squared sine kx. So this gives me my condition of giving me a psi with a negative. So basically I can say negative k squared a sine kx. So this follows the condition of giving me a negative, giving me a k squared, giving me my psi back. So we know that works. And we know kx works as the argument. So now I need psi I of kx to equal 0. So that means that a sine kx equals 0. So kx must equal n pi, thus k equals n pi uh, uh, over x. And so now my psi I kx becomes a sine n pi x over, oh, I have to put my a, which I always do. So for a, there we go. Boom. Going back to our original equation. And I should just say psi of x equals that. And since k equals n pi over a, and k from here, so k squared equals n squared pi squared over a squared, and k squared from here equals 2m e over h bar from here. So equating these, my energy is going to be n squared pi squared I forget the square. Yeah, that's off my square here. Did I leave that off anywhere else? Nope. And squared pi squared h bar squared over 2m a squared. That's my en. So we have everything we need now to plug it back into the original equation and have the proper one. So all of that was basically an aside to get what we need. So I'll highlight this all blue. So that's that. So that means that I can plug this in and see this equals 1 over square root of 2. That's my a value. And sine of, oh, hold up. I need to get a normalization factor for just sine as well. So that was the importance of getting this part worked out. So that's why we needed the energy thing as well. So going back here, it tells us in the problem that we have an even mixture of the first two stationary states. So that means that this is going to be E1 and E2. So E1 equals pi squared h bar squared over 2m a squared, and E2 equals 4 pi squared h bar squared over 2m a squared, which equals 2 pi squared h bar squared over m a squared. So E1 equals pi squared h bar squared over 2m a squared, and E2 equals 2 pi squared h bar squared over m a squared. And that's our two energy states. But at the same time, I need to normalize. So I guess I should properly call this. So this A here was the A for the combined state. So I will call this A prime. So that means that each of these states has to equal 1. So from 0 to A, I should say psi I x squared. That needs to equal 1. So we have integral from 0 to A of A prime sine of n pi x over A. Oh, and actually I should do let's do psi 1. I can have a definite 1. So psi 1. So that's A sine uh pi x over A. And I could actually call this A1, right? And this is going to be mod squared dx. So since there's no imaginary part, it's going to be 0 to A of A1 squared sine squared n pi over A. excuse me, pi x over a dx. And I know there's an easy way to integrate this. I believe it's 1/2 is what it is. Yeah, because I don't remember. I believe it's always 1/2. I don't remember exactly how it's always 1/2. Let me look that up really fast. Well, I mean, I could just take the integral. It's not a big deal, really. So this is going to be a squared integral from 0 to a. And this is going to be 1/2 plus minus cosine of 2 pi x over a over 2 dx. If I'm remembering that correctly. So this will be a1 squared, and this will be x over 2 minus sine 2 pi x over a divided by 2 times 2 pi. It should be an a, 0 to a. So this equals a squared a over 2 minus 0. So this equals a squared a over 2. I believe that's right. And this equals 1. So a squared equals 2 over a. So a equals square root of 2 over a. And let me see if that's the answer they had. Yep, that's the answer they have. So I guess that was close. What did I say it was? 1/2? Uh, I guess I would have left off this variable if I just did 1/2. So not bad to just do the integral. All right, so this is my a. So I have to remind myself that we must normalize how do I call it? Psi x 0 and 2 normalize psi I x, with the understanding that psi x0 is a sum of psi I x I to n, right? So my full psi up here is the sum of those sub-equations, a linear combination of those. Those are the energy eigenstates. So, and as we were discussing earlier, you could build up any function from the energy eigenstates. So these are the energy eigenstates. And this is the uh, full psi, albeit at t equals 0. So we have to normalize the full psi. Then we have to normalize each of the subsides. So that's crazy. That's what it is. So now think I have everything I need to make this a full equation. Make sure I didn't miss anything. I think it's odd that we can normalize the full psi without already knowing the subsize. Like I think normally in normal classical math, we find out the values of the subparts and then build up from there. But apparently in classical mechanics, you start with the overall equation, the overall psi of t, and then you work down. Let me get my bottle of water here, right? So in classical, we start from the overall. Then after we get the overall, I guess technically because I mean, it seems like it would affect the larger one. I'm not so concerned about it that I'll go through that whole calculation. But it seems like now that I've normalized the sub-equations, well, one of them at least, I just have to normalize the other one. But what will that do differently? Yeah, we'll actually change it a bit, will it? Let me look at the solution and see if the sub-normalization changes much. Now this would be the same for, so I'm not exactly sure how. Because if I were to put a 2 here, then this would be a 4, and this would be, oh, that's because that whole term disappears. This would be a 4, this would be a 4. And at A, that's still 0 on the right side. So it does zero out no matter what. So same answer for uh, side 2. I'll give you the same answer. Right? So that works out. So we normalize the overall equation, which is the sum of those. We normalize each of the separate ones. And now my psi xt equals, I'll say A psi x0. So that equals A sum of I to the n psi I x. So that's going to equal A. In our case, it goes to 2. So it'll be A1 psi 1 E negative I E1t over h bar plus A2 psi 2. And actually, I left off the uh, exponential part in the writing. E negative I E I t over h bar. And this would be also summed up the E negative I E I t over h bar. So this would be A1, A2, and E negative I E2 t over h bar. So now I can plug everything in. So A was 1 over square root of 2. A1 here. A1 equals A2. So this becomes square root of 2 over A, and A1 was sine 1 e to negative I E1 t over h bar plus square root of 2 over A sine 2 pi x over A e negative I E2 t over h bar, and close that. Take a look and see what we have. So 2 over A sine pi x over A e to negative. Now, they do some, they take some mathematical liberties here, and they say, allows to simplify E1 equals, where did I put the E here? We're gonna call this, what? Second color. So E1 is that, E2 is that. I'll just copy this down. So this would be E negative I E1 C over H bar equals E negative I squared H bar squared over 2 H squared T over H bar. And they're going to let omega, naturally let me cancel some stuff first. So this omega squared will cancel with that omega. This will be E negative I squared H bar over 2m A squared T. And they're going to let omega equal pi squared H bar over 2m8 squared. So omega equals pi squared H bar over 2m A squared. Okay, real kindness. Good seeing you, man. I should be here throughout the day. Give me one moment. We have all of this worked out. Boom, boom, side here. Right? So we're plugging in our energy. So now we have pi squared, h bar squared, h bar pi squared, 2a squared equals e negative I omega t. So then we have e I e2 t over h bar. That's going to equal double the first one. That's going to be e negative 2 I omega t. Hold up. What's that? It's 2 squared. So this would be 4. 4. It's 4 times the first one. That's the thing. Hold up. It doesn't linearly change. So e, therefore, e negative I e1 t equals e negative I omega t, and e to the I e2 t equals e to the negative 4i omega t. So that equals 1/2 these equals 1 over square root of 2, square root of 2 over a sine pi x over a uh, e negative I omega t plus root of 2 over a sine 2 pi x over a e negative 4 I omega t. All right, so that's my equation there. And I'll have to remember the trick that we can make omega define omega as pi squared h bar m over a squared. Remembering that a is not squared, right? Did you suggest that in the problem? Yeah, it did. Express the latter as a sinusoidal. Find psi of t and psi squared of t express the latter as a sinusoidal function of time. As an example, 2.1, simplify the result. Simplify the result and let omega, define omega as pi squared e squared over 2ma squared. All right, so that's that. Now we have the full psi. So I can actually call this a normalized general and specific. I think that's official terminology, but that's how I will call it. All right, so we have that worked out. And what I'll do is take a break, and then we'll come back and do the psi squared. So I'll see y'all in a bit.